The other day, I was in the drive-thru for Chick-fil-A and I was a little bit bored. So I started counting the wait time between cars at the window. And I checked with the cashier when I got to the window and I asked them if they had collected that type of data. And they said that they, in fact, did collect data for wait time at the drive-thru window. And I imagined that they would be interested in finding out the mean wait time for someone in the drive-thru. The variable wait time is a quantitative variable. And we talked in the previous chapters about how to find a confidence interval for a proportion and how to do a hypothesis test for a population proportion. So in those cases, the variable of interest was categorical. So what we're going to focus on now is how to find confidence intervals and how to construct hypothesis tests when the variable of interest is quantitative. All right. And so again, it would be nice if I could get the Chick-fil-A data to actually be able to construct the confidence interval. But in fact, I did check with a friend who works with Chick-fil-A and they don't release that data to the public. So anyway, but I hope you can sort of imagine that this type of calculation is of interest to companies. This is just one example. All right, so we're going to start to talk about how to construct a confidence interval for a population mean. And the process we're going to use is very similar to what you saw for the confidence interval for a population proportion. We're going to start with a point estimate, which is the sample mean, and then we're going to add and subtract a margin of error. So I'm just going to abbreviate that, MOE for margin of error. Now, before I go any further, we might want to take a moment and just remind ourselves of some notation that we use. Let's recall that X bar refers to a sample mean. All right, so in my Chick-fil-A drive-through scenario, I collected data for about 10 cars. So my sample mean would be based on the wait times for the 10 cars that I had data for. Now, what we might be interested in is a population mean. So that would be the mean wait time for all cars that go through the Chick-fil-A drive-thru. All right, and that's going to be something that we're probably not going to get data for every single car. So we're going to have to estimate it with a sample mean. All right, we might also look at the sample standard deviation. So we use S for the sample standard deviation. Okay, and then our parameter sigma represents the true population standard deviation, which is usually an unknown value. Think about it. If we're trying to estimate the population mean mu, then we probably don't know the population standard deviation sigma either. Okay, so in practice, we don't know the population standard deviation. If we don't know the mean, we probably don't know the population standard deviation. So when you look at this formula that I showed you for the confidence interval for population mean, notice that it calls for sigma. Notice that sigma is in that equation, but this isn't going to be a very helpful equation if I don't know sigma. So what we do in practice is that we substitute the standard deviation S, the sample standard deviation S, for sigma. All right? So that's all fine and good, but the problem is this introduces extra error because S is only an estimate of sigma. So we're going to use a fix for this. To account for this increased error, we are going to replace the z-score by a slightly larger score called a t-score. And then the confidence interval becomes a bit wider. This distribution is called the t-distribution. And we're going to talk for a little bit about the t-distribution. All right, so again, the reason we're looking at the t-distribution is because the t-distribution is going to be a way for us to compensate for the fact that we're using S instead of sigma. It's going to put a little tweak on the equation to account for that extra error. All right, let's take a look at some properties of the t-distribution. The t-distribution is bell-shaped and symmetric about 0, just like the standard normal distribution is. Its probabilities depend on the degrees of freedom. All right, so we actually have infinitely many t-distributions, and we're going to use the t-distribution for the appropriate degrees of freedom for our particular sample. Degrees of freedom is actually very easy to determine. It's just our sample size minus 1. The t-distribution has thicker tails than the standard normal distribution. That is, it is more spread out. I'll show you a picture of this in a minute. And when we are working with the confidence interval, a t-score multiplied by the standard error gives us the margin of error for a confidence interval for the mean. All right, so you're going to see in a moment that what we're going to do is we're going to replace this z-score. We're going to replace it with a t-score when we use S instead of sigma.